if you stood trial in the United States after 2013, then there's a decent chance that part of the decision was informed by an algorithm. At that time, and for several years after, judges could consult COMPAS, an algorithm that predicts whether a defendant is likely to reoffend in the future. Based on these forecasts, judges made decisions ranging from the length of bail sentences to the bail amounts for release. However, there was a serious issue with these risk scores. Black defendants got systematically higher risk scores than white defendants. And in fact, for violent crimes, black defendants got risk scores that were too high twice as often as white defendants. As a result, they received longer sentences and higher bail amounts than they should have, and that for a system that, in the end, didn't even work that well. A later study found that COMPAS is about as accurate for risk assessments as the average layman. The challenge now is to avoid such biases in other algorithms that are developed. Here, there's a bit of good news. We have a range of techniques to ensure that algorithms are fair, that is, free from bias. However, to use these solutions, we must give clear mathematical definitions of the type of fairness we want to enforce. Only then is it possible to test algorithms on fairness and to adjust their behavior. So, where do we start? Historically, the first idea is that we are fair when we don't base our decisions on protected features. In other words, discrimination happens when you make a decision based on someone's gender, nationality, ethnicity, and so on. As a result, gathering data of this type needs to be justified if it is even allowed in the first place. However, this kind of fairness through unawareness, where we avoid bias by not supplying certain information, is usually not enough. Machine learning algorithms in particular are very good at using correlations, such as those between zip code and nationality, to still make biased decisions. As a result, we need these mathematical definitions of fairness to ensure that there is no problematic bias. Here, it helps to begin with the notion of demographic parity. This statistical fairness measure maintains that an algorithm is fair if the probability of a positive decision is equally high for both groups. For example, a hiring algorithm is fair in this sense if it recommends equal proportions of men and women. The loan approval algorithm you see visualized on the slide is fair if it gives loans to 50% of group A, say to men, and likewise to 50% of group B, say women. As you can also see, this doesn't necessarily mean that it will be making the right decision all the time. Perhaps giving a loan to 50% of group B means giving lots of loans to those who cannot afford it, simply to get to the 50% approval rate. Not only can that feel unfair, it can also be detrimental. People who cannot afford loans end up in debt and are usually worse off than if they hadn't gotten a loan at all. So we should look for alternative measures to capture this disparity. And perhaps accuracy will help here, such as the statistical measure known as equality of opportunity. Here, it is not the overall acceptance rate, but the percentage of correct positive decisions that should be the same. So, in healthcare, that can mean that when someone has a disease, it is correctly diagnosed by the AI equally often for both men and women. And in our loan example, it means that when someone can afford a loan, he or she is given one equally often. You still see that this doesn't take into account the mistakes made by the algorithm, and that consequently there's a disparity in the number of incorrectly approved loans between the two groups. Therefore, it's a good idea to look not at the true positive rates alone, but also at the false positive rate. If you're very ambitious, then you can even combine the two into the statistical measure known as equalized odds. As you can see on the slide, the differences in mistakes disappear, and the algorithm will have equal probability of correctly approving a loan and of incorrectly approving a loan. Yet, it also has the consequence that fewer loans are approved in total, making financing a home much more difficult. And as you can see, it implies that we no longer adhere to demographic parity. This will be the case in almost all situations, as the different statistical fairness measures are incompatible with each other. We cannot be fair in all ways at once, and we have to choose between these measures. They also aren't perfect, as important aspects of fairness can be missed by statistical measures. They don't take into account the cost of fairness, as enforcing statistical fairness hurts accuracy and thus results in fewer correct decisions being made. That can be unfair under a more philosophical and less statistical understanding of the notion. So, while fairness measures help to reduce problematic biases in algorithms, they are not a silver bullet.